Proxima Centauri, the nearest star to our solar system, has long captured the attention of astronomers. This diminutive red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, forms part of the Alpha Centauri star system, which also includes Alpha Centauri A and B. Despite being only 4.24 light-years away from Earth, Proxima Centauri is not visible to the naked eye because of its faint luminosity. Nevertheless, Proxima Centauri holds tremendous scientific significance, particularly as the host star of Proxima B, an exoplanet that orbits within the star's habitable zone. Red dwarfs, like Proxima Centauri, are smaller, cooler, and have far longer lifespans than stars such as our Sun due to their low luminosity. These stars are difficult to observe, but this also means their habitable zones are located much closer to the star itself. For Proxima Centauri, this proximity translates to an orbital distance of just 0.05 astronomical units, a fraction of the distance between Earth and the Sun. This close orbit subjects Proxima B to intense stellar activity, including frequent solar flares and high radiation levels, making its environment starkly different from Earth's. The discovery of Proxima B marked a significant milestone in exoplanet exploration. By utilizing the radial velocity technique, astronomers detected minute wobbles in Proxima Centauri's position, caused by the gravitational tug of an orbiting planet. These wobbles enabled scientists to estimate the planet's mass and orbital characteristics. In 2016, the European Southern Observatory officially confirmed the existence of Proxima B, marking a major advancement in the quest for potentially habitable worlds beyond our solar system. Although ground-based telescopes have contributed valuable data on Proxima B, they are limited by factors like atmospheric distortion and light interference, which hinder detailed observations of the planet's surface or atmosphere. Most of the information we have gathered so far, such as the planet's mass, distance from its star, and orbital details, is based on indirect measurements. To further understand Proxima B's environment and its potential for harboring life, more sophisticated tools such as the James Webb Space Telescope, JWST, are essential. Proxima Centauri plays a pivotal role in the exploration of exoplanetary systems. As the closest star to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, in particular, presents an exciting possibility. A rocky, Earth-sized planet with the potential to support liquid water, and perhaps even life. However, the extreme conditions on Proxima B complicate the task of assessing its habitability. The James Webb Space Telescope is not just another instrument in the astronomer's toolkit. It represents a revolution in our understanding of the universe. Designed to succeed the Hubble Space Telescope, JWST was conceived to overcome the limitations of its predecessor and push the frontiers of human knowledge. While Hubble has provided invaluable insights into the cosmos, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, on the other hand, is optimized for infrared observations, enabling it to peer through cosmic dust and reveal phenomena that are invisible to Hubble. A standout feature of JWST is its primary mirror, which measures an extraordinary 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror allows JWST to gather significantly more light, giving it the ability to observe even the faintest and most distant objects. Coated with a thin layer of gold to improve its infrared reflectivity, the mirror is made up of 18 hexagonal segments that work in unison to create an exceptionally sensitive observation platform. Another groundbreaking innovation is JWST's 5-layer sunshield, which ensures the telescope's instruments remain at an ultra-cold temperature of approximately -233 degrees Celsius. This frigid environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST is positioned at the second Lagrange point, L2, about 1.5 million kilometers from Earth. This location minimizes interference from the planet's heat and light, enabling JWST to maintain continuous observations. JWST can study a wide range of cosmic phenomena, from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its focus on infrared light is especially valuable for studying redshifted objects, those whose light has been stretched into longer wavelengths due to the expansion of the universe. JWST's capabilities go beyond mere observation. The telescope is designed to address some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that might support life on other planets. With its state-of-the-art instruments, including the Near-Infrared Camera, NIR-CAM, the Mid-Infrared Instrument, MIRI, and the Near-Infrared Spectrograph, NIR-SPEC, JWST is not just a telescope, it's a time machine, a laboratory, and a testament to human ingenuity. Proxima B has fascinated both scientists and the public as a potential second Earth. Positioned within its star's habitable zone, the planet may have the right conditions to support liquid water, a key ingredient for life as we know it. With a mass approximately 1.17 times that of Earth, Proxima B is likely a rocky world, similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from a perfect replica of Earth. One of its most striking features is its tidal locking, meaning one side of the planet is in constant daylight while the other remains in perpetual darkness. This results in extreme temperature differences between the two hemispheres, with the region at the terminator line, where day meets night, offering a potential twilight zone where conditions might be moderate enough to support life. Despite its potential, Proxima B faces significant challenges. Its host star, Proxima Centauri, is a red dwarf known for emitting intense solar flares, which release high levels of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains an atmosphere, it would likely need a strong magnetic field to protect it from radiation. Without such a shield, its surface could be inhospitable to life as we understand it. Despite these harsh conditions, scientists remain optimistic about the potential for life on Proxima B. The planet's location within the habitable zone suggests that liquid water might exist, either on its surface or beneath the ground. Life might adapt to these extreme conditions, much like extremophiles on Earth, organisms that thrive in hostile environments such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima B is not only a scientific endeavor but also a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima B represents an intriguing possibility, an Earth-like planet that might harbor the necessary conditions for life. As technology advances, so too does our ability to explore this captivating planet and uncover its mysteries. Although Proxima B offers tantalizing possibilities, its environment is deeply influenced by its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf star, smaller, cooler, and far less luminous. Its reduced size and temperature result in a habitable zone that is much closer to the star. For Proxima B, this means an orbit at just 0.05 astronomical units, about 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet, including frequent solar flares that release intense bursts of radiation. These flares could bombard Proxima B with high-energy particles, possibly stripping away its atmosphere over time. Without a protective magnetic field, the planet's atmosphere would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima B retains some of its atmosphere, the radiation from its host star presents significant challenges to life. High levels of ultraviolet radiation could break down molecular bonds, preventing the formation of complex organic compounds, which would limit the possibility of life developing or sustaining itself on the planet's surface. Interestingly, Proxima B's tidal locking might offer some protection. While one side of the planet constantly faces Proxima Centauri's radiation, the dark side could serve as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Additionally, if Proxima B has subsurface oceans, these could offer a stable, radiation-free environment where microbial life could thrive, much like Earth's deep-sea ecosystems around hydrothermal vents. Despite the challenges, scientists remain hopeful that Proxima B's extreme conditions provide a unique opportunity to study life's adaptability. By observing how organisms might survive, or even thrive, under such harsh circumstances, researchers can expand their understanding of what makes a planet habitable. Proxima B is not just a potential home for life. It's a natural laboratory for testing the limits of life itself. The planet's proximity to Earth and its location within the habitable zone of its star make it an ideal subject for further investigation. With new telescopes and instruments, scientists will continue to monitor Proxima B for signs of habitability and life. Though the road ahead is fraught with challenges, Proxima B offers an exciting glimpse into the possibilities of life beyond Earth. It serves as a reminder that our quest for knowledge and the search for life on other planets is just beginning. The study of exoplanets like Proxima B plays a crucial role in expanding our understanding of the conditions necessary for life to exist. One of the key factors making Proxima B so intriguing is its Earth-like size and composition, which make it a prime candidate for studying the potential habitability of planets outside our solar system. Scientists are particularly focused on finding planets with characteristics similar to Earth's, as these offer the best chances for life to evolve. To further investigate the possibility of life on Proxima B, astronomers are employing cutting-edge techniques to analyze the planet's atmosphere and environmental conditions. One promising method is transmission spectroscopy, which involves observing how light from a star passes through an exoplanet's atmosphere during a transit. This can reveal the chemical makeup of the atmosphere. By analyzing absorption lines in the light spectrum, scientists can detect gases like oxygen, methane, and carbon dioxide, chemicals that are often associated with life on Earth. Detecting such gases on Proxima B could offer compelling evidence that the planet supports biological processes. Researchers are also exploring the possibility of microbial life beneath Proxima B's surface. The idea of subsurface life has gained traction, especially with the discovery of extremophiles on Earth, organisms that thrive in environments once thought inhospitable, such as deep-sea vents or acidic lakes. Subsurface oceans or aquifers could provide a stable, protected environment where life could thrive, shielded from the harsh radiation and solar flares that bombard the planet's surface. In addition to the search for life, Proxima B offers a unique opportunity to learn more about the broader processes that govern planetary systems. Its location within the habitable zone of its star provides an excellent opportunity to study the interactions between a planet and its host star, and how these interactions influence a planet's ability to sustain life. For example, the frequent solar flares from Proxima Centauri may play a significant role in shaping Proxima B's atmospheric conditions. These flares could affect the planet's climate, weather patterns, and magnetic field, all of which are essential factors in determining whether the planet could support life. While research on Proxima B is still in its early stages, advancements in observational technology, such as the James Webb Space Telescope, are offering new tools for scientists to probe deeper into the mysteries of the exoplanet. JWST's infrared capabilities will allow for more detailed studies of the planet's atmosphere, surface, and potential signs of habitability. As our understanding of exoplanets evolves, Proxima B will remain at the forefront of efforts to answer one of science's most profound questions. Is there life beyond Earth? Ultimately, the study of Proxima B is not solely about finding alien life, but also about learning more about the conditions that make a planet habitable. By understanding the factors that contribute to a planet's ability to support life, scientists can apply this knowledge to other exoplanets in the future, broadening our search for life in the universe. The exploration of Proxima B is just one step in a much longer journey to uncover the vast and mysterious world of planets beyond our solar system. Proxima B's study also helps us understand planetary formation and the evolution of star systems. By examining the relationship between Proxima B and its host star, Proxima Centauri, astronomers can gain insights into the dynamics of planets orbiting red dwarf stars. These stars, which make up most of the stars in our galaxy, present both unique challenges and opportunities for planet formation. Understanding the interactions between red dwarfs and their planets, particularly in relation to stellar radiation and magnetic fields, will provide valuable information about the types of planets that can form in such environments and their potential for habitability. Furthermore, Proxima B's proximity to a nearby star system raises intriguing questions about planetary movement and migration. It's possible that Proxima B originated farther from its star and gradually migrated inward over time. Studying the mechanisms behind such planetary migration could shed light on how habitable zones in other star systems evolve and shift over billions of years, potentially altering the conditions for life on planets like Proxima B. As we continue to explore exoplanets, Proxima B remains a key piece of the puzzle in understanding where life might exist beyond Earth. Its study offers a glimpse into the future of exoplanet research and the broader search for life in the cosmos.